Okay, now this is the continuation of the lesson on cyclic quadrilaterals. We're going to prove the cyclic quadrilateral theorems, and we're also going to do some examples on cyclic quadrilaterals. So here is the first theorem that we looked at, Sokol theorem 9, that the opposite angles in a cyclic quadrilateral are supplementary. In this case, for example, we're going to prove that angle A plus angle C is equal to 180 degrees. So, to start the proof, we've got the centre of the circle O there, and we're going to join BO and DO. So I'm just going to do that now. So we're joining BO and DO. Now, if I, what I'm going to do, what we can see is that angle A, okay, so we've got angle A up there, that's the angle at the circumference, and we've got that angle BOD, the obtuse angle BOD, so that angle down there, equals twice the angle at the circumference. So I've got that obtuse angle BOD equals 2 times angle BAD, okay, or just 2 times angle A, because the angle at the centre is twice the angle at the circumference. I'm going to put on arc BCD. Now I'm calling it arc BCD so that we know that it's the minor arc. Okay? Now, what we're also going to do is we can actually also work out this reflex angle BOD. All right? But before I do that, I am going to do that. The way we can do that is that we know that reflex angle BOD plus obtuse angle BOD, so reflex angle BOD plus obtuse angle BOD equals 360 degrees because it's angles sum at a point or angles in a revolution. So there. Now, actually, there's a little step that I need to insert there as well. But we also know that reflex angle BOD, this angle there, is 2 times angle BCD, which I'm just going to write as 2 times angle C. And up here, where I've got obtuse angle BOD is 2 times angle BAD, I'm just going to say, well, that's really 2 times angle A. Okay, because there is no ambiguity as to what angle A is, because there's only one angle at A, and there's also no ambiguity for what angle C is, because there's only one angle at C. So going back to this equation here that I've starred, reflex angle BOD, because we know that it's 2 times angle C, so I'm going to replace that with reflex angle BOD is really 2 times angle C. And obtuse angle BOD we know is 2 times angle A, and so therefore 2 times angle C plus 2 times angle A is 360 degrees. So I've basically substituted all of that into that equation with the asterisk. Now if I take out 2 as a common factor, so I get 2 times angle C plus angle A is 360, therefore angle C plus angle A is 180 degrees, and therefore we have just proved that the opposite angles, which are A and C, of a cyclic quadrilateral are supplementary. Now we could have also done this and proved that angle B plus D also adds up to 180 by, instead of joining OB and OD, we could have joined OA and OC. Okay, so I'll just write that down there. Similarly, that we can prove that angle B plus angle D equals 180 by joining OA and OC, and obviously doing the same process as what we've just done above. Okay, now this is the proof of Sokol theorem 10, that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. So basically what we've got to prove is that angle BCE is equal to angle DAB. So what we're going to do, we're going to start by letting angle DAB equal X. Okay, Now, because of the theorem that we just did, which is Sokol theorem 9, in that opposite angles of a cyclic quadrilateral are supplementary, we therefore know that, so we know that angle, so if this angle up here is x, then angle DCB equals 180 minus x, because that angle there at C, angle DCB plus angle DAB equals 180. Reason that the opposite angles of a cyclic quadrilateral are supplementary. Okay, so I'm just going to write that in there, that this angle here is 180 minus x. Now, remember, we're trying to work out angle BCE. So angle BCE will be 180 minus whatever angle BCD is. And that is angles on a straight line or supplementary angles, whatever you like. So I'm just going to put angles on straight line, and I'm going to call that line the DCE, okay, because the straight line runs from D through C to E. So therefore angle BCE is 180 minus, I'm going to substitute what angle BCD is, and it's 180 minus x. Now we can expand and remove those brackets, so we get 180 minus 180 minus negative x, which is plus x. Therefore angle BCE is equal to x, which is what we are required to prove. So therefore we can say that angle BCE is equal to angle DAB, and therefore we've proven that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Okay, now we're looking at page 18 of the work booklet, and we have to find the value of the pronumerals giving reasons. So we can see that we've got this angle here that's 20 degrees. We also know that OB is equal to OD, and that this angle here would be 20 because we've got an isosceles triangle. So we could work out A that way by doing angle sum of an isosceles triangle. We still need to work out C and B. We can see that angle A is the angle at the center, B is the angle at the circumference, so we know that B is half of A. And we know that C is also the angle at the circumference, but it will be half this reflex angle here at the center. So if you want, you can try that yourself. You can pause the video and then come back to the video just to check your answer. Okay, so I'm going to go that OB equals OD, reason equal radii. Then we can say that angle OBD equals angle ODB equals 20 degrees, reason base angles of, oops, I'm running off the page, just bring this out a bit. So we've got base angles of isosceles triangle OBD. Okay. We also know that A is equal to 180 minus 20 minus 20 because it's the angle sum of triangle OBD. Okay, I'm just running off the page a bit, so I've just fixed that, which happens to be 140 degrees. So remember, every time you write something, you do need reasons for every single thing. So we also know that angle B equals a half of 140 degrees, which is 70 degrees, because the angle at the circumference, I'll just move this over. Actually, I'll just bring this up a bit so I can see more. Okay. So the angle at the circumference, sorry about that, is angle at the center, should fix that up. So the angle at the center is twice the angle at the circumference on arc. It's going to be, that's the angle at the center there, angle at the circumference is angle BAD, so it's on this arc here, on arc BCD. So we've worked out what A is, we've worked out what B is, and now we just need to work out what C is. Now, before we can do that, we're going to need, we can see that that's the angle at the circumference, so we need the angle. Okay, so actually a bit of a difference to what I was going to do before. We know that angle B and C are opposite angles of a cyclic quadrilateral. So we're just going to say that angle B plus C is 180 degrees. Opposite angles of cyclic quadrilateral are supplementary. So therefore C is 180 minus B, which is 140. So therefore, sorry, actually it's not 140. B is 70. So therefore C is 180 minus 70, which happens to be 110 degrees. So that's your answer. And finally, I actually got there, doing it a slightly shorter way than what I originally thought. So, you know, sometimes you do forget some of your theorems. So look, there is always more than one way to do it, but it was obviously going to be quicker to do opposite angles of a cyclic quad here rather than doing the reflex angle there, and angle at the center is twice angle at the circumference. So we're going to do the next question now. Why don't you attempt it, question 2, and then pause the video and you can check the solution. Now, okay, we're actually just going to leave this question here for now, which is question 2. Sorry, I'll just focus it. So we're going to leave question 2 just for a minute because it is a little bit tricky, and we're going to go to the next page, okay? Okay, what we're going to do, we're going to firstly look at the 3 tests for cyclic quadrilaterals. Okay, now, the first test, we did briefly speak about these today in class, but we're going to formalize them now and write them down. Now, this is the first here, this is the first test here. I'll just put my piece of paper in, okay? Okay, so, again, 4 points are concyclic if one of the following tests is true. Now, we're going to look at the 3 tests. We did discuss this test today because it was the converse of one of the theorems. Now, here is the first test. If one pair of opposite angles of a quadrilateral are supplementary, then the quadrilateral is cyclic, or we could say, which means if a quadrilateral is cyclic, that means that the 4 vertices of the quadrilateral are concyclic. So therefore, we could say then if alpha, so we can say, well, if alpha plus beta is 180, or if theta plus, I think it's, I can't remember the symbol for that, omega or something. No, I can't remember its symbol. It's not omega. If those 2 symbols are equal to 180, then I'll call this ABCD. Then we can say that quadrilateral ABCD is a cyclic quadrilateral. Okay, so that's that first test. Okay. All right, we'll go to the second test, or we could say that is A, B, C, and D are concyclic. Concyclic points, or we say A, B, C, D is a cyclic quadrilateral. All right, we're going to look at the second test now. Okay, now for test 2, which is this test here. And this test states that if one exterior angle of a cyclic quadrilateral is equal to the opposite interior angle, then the quadrilateral is cyclic. So I'll just write that down now. So just writing that down, for test 2, if one exterior angle of a quadrilateral is equal to the opposite interior angle, then the quadrilateral is cyclic. So we don't start off saying it's cyclic. What we say is that if this exterior angle here equals the interior opposite angle, then the quadrilateral is cyclic. Now, often when you get questions like this, the circle won't be drawn. You will just have a quadrilateral just lying there with no circle drawn. Another way we can say this is if angle BCE equals angle DAB, then ABCD is a cyclic quadrilateral. We're now going to look at test 3, which is over here. So this one here is test 3. And we can see that this is the converse of the angles in the same segment theorem. So I'll just write that one down. Okay, sorry, this is all bits of paper all put together. But test 3 is that if an interval, so that interval AD, if it subtends two equal angles, so if it subtends equal angles at 2 points on the same side of it, so there's the interval, and it's if we're saying that if alpha equals beta, okay, so if alpha equals beta, then the endpoints, those two endpoints and these other 2 points are concyclic. In other words, if alpha equals beta, then ABCD is a cyclic quadrilateral, or we can say that ABCD are concyclic. Okay, so I'll just move that up there. All right. So that is the third test. And as you can see in this diagram up here, there is no circle there for you to look at. Okay. Also, if we look back at test 1, there is no circle here for you to look at, but you know that if alpha plus beta is 180, then it's a cyclic quadrilateral. In test 2, all right, this diagram does have a circle, but often it will not have a circle. And if the exterior angle equals the interior opposite angle, then that also proves that that is a cyclic quadrilateral. And again, in the third one, no circle here can be seen, but if alpha equals beta, then the points A, B, C, D are concyclic, or A, B, C, D is a cyclic quadrilateral. So they're the 3 tests for cyclic quadrilaterals, and we're going to practice using those tests now. Okay, we're on page 20, and the first question 1 says, is A, B, C, D a cyclic quadrilateral? Give reasons. Well, we can see we've got the 2 opposite angles, so let's do 107 plus 73. Well, that is 180. Therefore, ABCD is a cyclic quadrilateral, and the reason is opposite angles of a cyclic quadrilateral are supplementary. Okay, now we will look at the second example here. Over here, look, we can see we've got this 37 there, and it's standing on, I suppose you can call it segment AB, okay? Or interval AB, actually, because we don't know it's sitting on a circle. So this angle here is sitting on interval AB, but this angle here, that's the angle that we want to be 37. So we don't know that this angle in here is 37. So we don't know that this is a cyclic quadrilateral. So we're going to say, well, based on what we've got there, no, it is not. Okay, it is not a cyclic quadrilateral, because if it was a cyclic quadrilateral, we would need, as angle BDA is not 37 degrees. Okay, so for the cyclic quad, for it to be a cyclic quadrilateral, we would need angle BCA to be equal to angle BDA, which is 37. But this is not the case. Okay? So we cannot say that it's a cyclic quadrilateral based on the information there that you've got. Okay, I'm just focusing that now. Okay, so no, it is not a cyclic quadrilateral, as angle BDA is not 37 degrees. For it to be a cyclic quadrilateral, angle BCA there would have to equal angle BDA to be equal to 37 degrees, and this is not the case. Okay, so we don't have that. Okay, we're going to look at the third example. So is this next one a cyclic quadrilateral? No, I don't think it is. It might be a parallelogram, but it is not, because opposite angles of a cyclic quadrilateral are supplementary. Now, if we add up the opposite angles in this quadrilateral, we can't call this cyclic because we don't know whether it is or not, but it is a quadrilateral. If we add up angle A plus angle C in our diagram, we get 87 plus 87, and that's definitely not 180. It's actually 174 degrees, which does not equal 180. So therefore, no, it is not a cyclic quadrilateral. Now we can look at example 4. Now here we can see that the exterior angle of this quadrilateral is equal to the interior opposite angle. So we can say yes, it is a cyclic quadrilateral, because we can see that angle BCE is equal to angle DAB, which is 113 degrees, and the reason is that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Okay, so that's reasons why that one is a cyclic quadrilateral. Okay, now looking at number 5, here we can see that this angle BAC is equal to angle BDA. So therefore, if we look at the interval BC, I know it's not drawn, but if it was drawn, we know that the interval BC subtends equal angles at 2 other points on the same side of it. So then those 2 points and the endpoints of the interval are concyclic. So we can say yes, it is a cyclic quadrilateral. And the reason is that if I'm just going to put that interval BC subtends equal angles of 41 degrees at A and D. So A, B, C and D therefore are, sorry, I'll just fix that up. So therefore A, B, C and D, so actually no, all right, so A and D and the endpoints of the interval B and C form a cyclic quadrilateral. Or actually we can say that they are concyclic points, okay? Okay. Now, of course, they would form the cyclic quadrilateral in the order A, B, C, D, not in the order A, D, B, C. It would be A, D, C, B, I suppose. Okay. All right, now with the next one. Okay, we have to see if we've got a cyclic quadrilateral anywhere, and we'd probably be looking here. Now, what we really want is to look at whether can we see an exterior angle anywhere of this cyclic quadrilateral, or can we see interior opposite angles being supplementary. Obviously, it isn't going to be angles subtended by an interval. Okay, so here is the quadrilateral there. I'm just outlining it there. Okay, we can work out this angle here. So angle D, actually I'm going to label this point as F. Okay, so I'm going to say angle DFA is equal to 80 degrees, reason vertically opposite angles are equal. And I can say, well, angle DEA plus angle DFA is 50 plus 80, which is 130. Now that does not equal 180. Therefore, we can say it is not a cyclic quadrilateral. I'll just move this down a bit. So it's not a cyclic quadrilateral. Move that up a bit. So it's not a cyclic quadrilateral, as the opposite angles of the quadrilateral are not supplementary. Okay, so that's page 20 done. Okay, All right, we're going to go to page 21 now. Okay, page 21 actually is still from that same series of questions, so we have to see whether we've got a cyclic quadrilateral or not. Now, we can see that interval DB subtends angle 75 over there and angle 75 down here, but angle A and angle C formed are not on the same side of the interval DB. Also, we can look 75, angle A and C are also opposite angles, but they are not supplementary either. So, and we don't have any exterior angle of this quadrilateral there, so we can't try that test. So we can say that it is not a cyclic quadrilateral. And the reason is that even though angle A is equal to angle C, which is 75, they are on opposite sides of the interval BD. Okay, to be a cyclic quadrilateral, the equal angles must be on the same side, of the interval BD. Also, angle A plus angle C equals 75 plus 75, which is 150, and that doesn't equal 180. Therefore, the opposite angles A and C are not supplementary. So that's another reason why, therefore, ABCD is not cyclic. Okay, it is not a cyclic quadrilateral. Okay, now we're going to look at the very last question. Okay, and this is the last question here on page 21, and we have to prove that ABCD is always a cyclic quadrilateral. And we've been given a hint to draw CX parallel to DA, so I'm going to draw that. Whoops, actually that's not drawn that well, so I'll just fix it up. So I have to draw CX, so I'll just put this other parallel line down there. So CX has to be parallel to DA, which I've done there, meeting AB at X. Okay, I'll just focus that again, it's just out of focus. Okay, now if I've drawn CX parallel to DA, then what I've got here is a parallelogram, because I've got one pair, two pairs of opposite sides parallel. We also know with a parallelogram that opposite sides are equal in length, so therefore DA would equal CX, which is equal to CB. I'm going to start putting some X's in here. Now I know here I've got an isosceles triangle. Sorry, I was unfocused again. So, as I was just saying, it's a parallelogram, so DA equals CX. We know that the length DC equals the length AX. I'll just put some indicators there. We also know that, sorry, this is just not focusing. We also know that CX equals CB because it's indicated there as well. And we also know that we've got base angles of the isosceles triangle there. Okay, so we're trying to prove that ABCD is a cyclic quadrilateral. So we've got to think whether we can find some opposite angles, supplementary or something like that. We'll just see what we can do. Okay, now if I let this angle here be X, then one sec, I'll just put this on autofocus, okay? So if this is a parallelogram, we know that opposite angles in a parallelogram are equal. So if that's x, then this is x. We would also know that this here would be 180 minus x because co-interior angles, these are parallel lines, co-interior angles add up to 180. So we'd also know that this up here would be 180 minus x. I'm just trying to work out how we're going to do this. We also know that this is 180 minus x because of angles on a straight line. So I actually probably don't need these bits here. I'm going to cross them out, okay? So what I've got is that I probably don't need those, as I said. So what I've got is, if I let this one up here be x, then that's x. This is a straight line, so this would be 180 minus x. This would also be 180 minus x because I've got base angles of an isosceles triangle. And so therefore, this angle here, x, plus this angle down here, 180 minus x, they both add up to 180 degrees. So therefore, ABCD is a cyclic quadrilateral. So that's how we're going to do it. So we're going to start off with saying, of course, we've done draw CX parallel to DA. Actually, I've drawn it to the wrong line. Oh, no, I haven't. So draw CX parallel to DA meeting AB at X, which we've done. So I'm going to say, therefore, so this is therefore, AXCD is a parallelogram. And the reason for that is that we've got two pairs of opposite sides parallel. Now, then I'm going to say, let angle ADC equal x. Therefore, angle ADC is equal to angle AXC, which equals x. Reason, opposite angles of a normal quadrilateral are equal. Then I can say, well, angle CXB is equal to 180 minus x. Reason, angles on straight line AXB. Okay, so I've got that this angle here is 180 minus x. Now, we know that we were given that DA equals CB given. But we also know that we also know that DA is equal to CX, opposite sides. Oops, I need some more room. So I've got opposite sides of parallelogram are equal. Okay? And so therefore, I can say that CX equals CB because they are both equal to DA. Therefore, angle CXB is equal, oops, I need some more room. So angle CXB is equal to angle CBX, which equals 180 minus x. Reason, base angles of isosceles triangle CBX. I'll just move this all up. I'll just move this back a bit too. So we've got base angles of isosceles triangle CBX, because of course we know that CX equals BX. So therefore, oops, we just need some more room. So therefore we can say that angle ADC plus angle ABC is equal to x plus 180 minus x, which is 180 degrees. And note as well that angle ADC is opposite to angle ABC, all right, in the quadrilateral ABCD. Therefore, we can say that ABCD is a cyclic quadrilateral. And the reason is, oops, just running out of room again. The reason is that, actually, the reason is if opposite angles, so the reason is if opposite angles of a quadrilateral are supplementary, then the quadrilateral is cyclic. Okay, and I think you can just see that. Okay, so that's the end of that proof. Okay, and so that's the end of that proof. So that's the end of those exercises on cyclic quadrilaterals. Okay, and so your homework is exercise 9.3 from the textbook. Question 1, HIJ. Question 2, all of it. They are all a little bit different, so I want you to do all of it. Don't forget to put all your reasons. And question 3, ABC. Actually, question 3 is quite easy. Okay, so that's the end of that video.